И так, ладно, начинаем. Начинаем тогда.
Я готова.
Так, а Наталья, как сделать, чтобы больше? Рафаэль нарисовал маленькие буквы. Как сделать больше?
Может быть, просто это окно, вот вы видите его у себя на компьютере, может, вы просто его сделаете на полный экран, и мы будем видеть только его. Ну,
Вот
как
так?
вы делаете? Да, например, так.
Ну,
Вот,
лучше.
так лучше? Так же лучше?
Нет, это я вас спрашиваю.
Нет, мне почти ничего не видно, но, может быть, можно еще так двумя пальцами в сторону по трекпаду, или если вы видите где-нибудь какой-нибудь плюсик.
Нет, он рисует.
On the top left, if you move the mouse, you have kind of I saw it, you know, the thing that to see this one, yes.
Thanks a lot. Yeah, there is a, but I don't think.
It's to search a word. No, you have a plus on the right.
Yes, it is not over there. It was the search. Okay.
Okay.
So, does everybody see?
Yes.
Okay. The idea of the was to make calculations, and so we are looking the calculations. This is what you are saying. So, Rafael, maybe you
to explain
yourself?
Yes.
Yeah.
So we start by doing a 3 coloring, and so we just make a 3 coloring on the top right, for example. It doesn't change anything, top right or top left or whatever. And then, so we arrive in this situation with 2 arcs that are not colored yet. And so we are trying to understand if it's possible. So let's take this arc here, and let's, for example, put it in red. So if we color it in red, it's already a problem because before we have a red, just before. So we don't have a 3 coloring. If we take it in green, we have the same problem. We already have a green. So the only possibility is to take this arc in blue. So let's take it in blue. And now we see that we already have another problem, which is here, if we take this one in blue. So we just understand that it's not possible to have a 3 coloring out of this knot. So we just take the trivial coloring for this one.
Yeah. So what is do you know how it is called, this knot?
Not at all.
1, 2, 3, 4, 5.
5, 1
Yeah.
maybe has another name, but
I think cinquefoil, quelque
chose comme.
Yeah.
Okay.
So, and what about algebra?
Algebra, so we will have, I didn't try the algebra here. So we will have just a big matrix, 5 by 5. And so we will take a minor and one of them. So I don't know. So if we call this one, x1, if we call this one x2, x3, x4, x5. So for example, here we will have the equation x1 plus x2 plus x5 equals 0, and so on, and we do it for every crossing, and so we will get a 5 by 5 matrix, and we will have that a minor 4 by 4 we will be different of 0 modulo 3. So we will get that the matrix is, yeah, that's it.
Very good. So let us go next. It is this guy. What are the?
So wait.
Yeah.
Yeah, it worked.
Yes.
Okay. So we do the same thing. We start by a tree coloring, no matter where. We just start doing one. So now we are looking at this arc. So if we take this arc in blue, for example, we have a problem here right away. If we take this arc in green, again, we have a problem here. Now, if we take it in red, we will have a problem here. So the problem is already solved.
Yes. So again, we don't have
we have only the trivial coloring.
Yes, that is okay, right?
Yeah. Here we are exactly in the same situation as the one we did last week. It's exactly the same. It's a different node, but algebraically or geometrically, it's the same situation. It was eighth node, if I'm not mistaken.
Right. Okay. You have the same, and and this is whitehead. Whitehead, it doesn't work, right? Because
whitehead. So let's again we can. So here, if we look at this arc, if we take in blue, we have a problem here. If we take it in red, we have a problem here. If we take it in green, we have a problem here. So again, we have a trivial coloring for this one.
Right. So and this is
here it works.
Right, here it works.
Here it works. So we have a tree coloring example here. And so we have 6 crossings, 6 arc, and algebraically each arc is just x1 plus x2 plus x3 with xi one of the color. So it's just dimension 5, if I'm not mistaken.
Yes, and so what is the invariant tau?
Tau is tau of this one equals to 5, if I'm not mistaken. Yes.
Sorry. What?
Yes.
Sorry. What is name of this node?
This I don't know. Maybe somebody knows.
6 something.
Yes, but this is not the name. This is the number. Maybe.
Number. Okay, maybe number. This is 623. But I think 3 up.
Is it a link? This is a link.
Yes, this is a two circle.
Yes.
But I think. Sorry. I think 6 3 2.
Yes, probably. That's why I wanted. Yes.
This is a number of circle.
Yeah, the number of circles should be over. And here we have only 2 circles.
2 circle. No?
2 circles, and first one in the ordering.
Yes. This 3 circle and ordering 2. No?
Yeah, number 2. So I don't see. So What is your remark, please? Can you precise?
Compared to the list,
another note, another link. This is this link?
Yeah, but anyway, it is beautiful. So just to, and you see how beautiful colors are. Just it doesn't matter which name it has. So if you remember precise name,
I think this is a free circle.
Free?
No.
I don't.
yeah,
I don't,
compare to the table of the table in lecture 4, the number here are flipped, if I'm not mistaken.
yeah, but anyway, it exists, so no problem.
Yeah.
Okay, thanks.
Okay, very good. So the picture, where is our, yes. So this is the, we shall look in detail for such notes maybe today, maybe next time, but it's called square.
Mm-hmm.
So what is the invariant for square? The T3 invariant, tau 3 invariant, how much it will be?
It will be 5 again.
No. I mean the dimension of vector space should be 2. It's,
wait, we have 3 intersection points.
right.
Sorry, 6 intersection points and 6 arcs as well.
Yes. But you see, here is a trefoil. This is the composition, which we'll look today. What does it mean? But intuitively, you see that this is a joint of
yes, two trefoil joint. Yes.
Yeah, but they are different. One and right and left. But anyway, it doesn't matter. So if you saw, better to explain like this. Why should I give this this example? Because it's simple from algebraic point of view. Look, in trefoil, you have 3 equations, but they actually give the same, right?
Yes.
And the same here.
Yes.
So,
okay.
So you see,
but if we look at it, here we have 6 equations, and all 6 are the same, or should be the same, no?
No. They there should be
different
equation here, but not all of them. Not all of them. Not all of them will be, but only some of them. Such a way that it should be that the dimension should be, as far as I remember, it should be 3.
Okay. Okay, but what I don't understand is here the equation is just x1 plus x2 plus x3, just same here as here. I don't see the different equation between them.
Okay, so maybe Natalia, did you look at this square knot? This is
I find free, power free.
Yes.
Yes.
That's what that's what.
And this and this, то есть blue and blue is the same color. Only one color. This line and this.
Okay. Understood.
And,
yeah.
and
Okay.
We can take right.
So
right
all
print
the
line.
So for example, this one. For example, this one is x1. This one is x2, and this one is x2 prime. For example.
No,
that's why
let it be x3.
x3. Yeah, x3.
Or better
okay.
to say, let it be x4. Let it be continue the same way. Let it be x3 here, x1, x2, x3, x4, x5, x6.
We have 6 variables.
Yes, 6 variables, 6 equations, and only 3 of them are essential.
Yeah. Okay. Understood.
Because as in trefoil, you see that there will be equations. Some of them will be the same.
Yes.
The idea.
Yeah. Understood. Thank you.
Yeah. So why I gave this example? The previous example were to see that this invariant is in most cases it is not a big number, but here it is 3. It is 3. So how of this, I write symbolically the square, not like this, is equal to 3. So it's a big number, right? Because you were previously considering that in many cases it is just only trivial. It means that tau is equal to 1. Okay.
Yes.
Natalia?
Yes.
Do you know the reason why it is equal to 3?
Why?
Yes.
Okay. Okay. Let's try. Let's try color.
Yeah.
We have this line is blue, but we can take any color.
Right.
But this line, same color in this blue line in this picture have one color.
Right.
We take in green line, take free this and this, and only three variables, and
Yes.
color.
Yes. Very good. Very good. So, very good explanation. So, if there are no questions, let's go further. Okay. Yes. Now let us understand what we were looking last time, the alternating and the graphs. Alternating and graphs. So, Raphael, can you? As for me, I like to explain this by pictures. So
yeah, picture is very
there
easy.
is a place. Maybe you can make a drawing here of this graph and picture. Why alternating gives us all the time? It gives us the constant. So if we just what we are calling the plus or minus, if we formalize this by a function, +1, -1, so you see that if and only if our link is alternating, the graph, the function is constant. This is what is interesting fact. Okay, can you make a picture here, Rafael?
Yeah. So if we have an alternating node or link, what's happening? So we have this here, it's enough, and that means that each crossing will be of this way, for example, or we can have hop. This is the only two possibilities. Because wait, yes.
Yes, but alternating, you should have this and this. If you are making alternation when you are going this way, you should, and you just color the domains and you'll see. Okay.
It's so wait, we are
Say we want to color this black, and we make our, this is positive direction, so this is black, right?
Yeah, it is. But so what do we look? We always look at how the over arrow is situated compared to the under arrow. The top arrow, if the top arrow is counterclockwise compared to the down arrow, it's -1, and if it's clockwise, then it's +1.
Vice versa.
Vice versa. Yeah.
Vice versa, Rafael. In the complex plane, we always consider this direction as a positive one, from real to imaginary. This is positive.
Okay. I took the
so
other.
This, for example, if we consider it is convention. So if we consider black, then for black graphs we take this as +1, +1 here, right?
Yeah. Wait. Over. Because if we look the over arrow here, it's clockwise compared to the under arrow, so it's +1.
Right.
Yeah.
You put a vertex here, you put a vertex here, it will be +1.
Yes.
This will be white, this will be white. So now here, look this crossing. And because again, in the positive direction is here, so you should, if you see the chessboard coloring, you should put this to this one. I don't know how to color to the other thing, to this one. You should put again +1. And so it depends the convention of colors, but now we are considering the blacks as our graph, as Natalia explained us that white will be dual graph. So this always we have if and only if our think our crossings is alternative, it will be everywhere +1. The same way, if we consider with respect to white ones, we'll have what? We'll have with respect to white, we'll have here clockwise, and clockwise, as you see, this is -1. So here you will have -1. And again, when you are crossing alternatively, it will be constant. So it's quite geometric proof. You need to move several ways, and it's done.
Mm-hmm. Yeah.
Very good. So, Natalia, do you want to add something? And okay. You have some remark, Natalia?
Oh.
No, let's continue. So I have again this problem.
Sorry, I think if we take white vertex, white arrow as vertices,
Yes.
we have same sign, +1 or -1.
Yes,
It's
but here in the picture, it is. Oh, this is the previous stuff. I don't need it. There will be -1 in the picture that we were looking, because it was like this.
maybe I understand how you calculate +1 or -1. We
Yes, you are right that this is convention. It may be +1, -1. The essential is that if link is alternating, it will be always constant. This is essential, right?
and maybe I can't understand your proof. We need arrow on all maybe on 2 line.
Okay, so the proof was like this. It is not necessary to consider the whole. Just look at these pictures. Look at this picture.
How you calculate +1 or -1? If we have this and this black,
Right. Right.
we have -1. Yes?
No. It depends. It depends which graph you should decide. You are considering graph with respect to blacks or graph with respect to whites. Okay.
Okay, this is age. We have 2 vertex, this, and 1 age.
Right. So it means that you are considering graph with respect to black.
Yes, this is this graph to respect to black.
Very good. So
we
then
have -1. We have -1 in this situation.
right. Right.
This upper and this down.
Right. Exactly. With respect to black, we have this direction. And this is clockwise, this is -1. But now imagine that you are... Sorry? Okay?
Respect black, okay, yes.
And now respect to white. You consider now the white domains and you put the vertex of your graph with respect to white. So we are now white, right? So you have 2 vertices and you have 1 edge because this is crossing, right? Now consider what happens here. Here, this is overcrossing in these two domains, white. But here, overcrossing goes to the positive direction. So this is the black one, part of the graph, and the white is the following: this one, and this one, and this one, and this will be +1. Because here it becomes positive. It's quite natural because this is these are 2 complementary domains. If in one this and this it is negative, then in the complementary domain it will be positive. So this is the black graph and this is the white graph. Black will always be negative, white will always be positive. Right?
Okay.
And these are two dual graphs, as you taught us. You are teaching us that they are complementary. And they are complementary not in the sense as the planar graph, they are also complementary that they are, one has pluses and another has minuses. If our knot diagram is alternating. Okay?
Okay.
Very good. So can we go further?
Yes.
So let us, to consider graphs. So Natalia will check us whether we are okay in constructing these things.
Okay.
And this is exactly what we have. Now this is not black, it is yellow, right? We are considering
yes.
the cinquefoil, and you have exactly this beautiful pentagon, right?
Mm-hmm.
Here in our wonderful figure 8, we have this thing, and this will be the graph. So, but let us construct the dual. Natalia, can you help us to construct a dual for cinquefoil? We have only 2 vertices here, right?
I cannot see about.
You see the file?
No, I cannot see. Yes, this I have four vertices
No,
cycle.
only two. Only two.
Two vertices.
The graph has only two vertices.
Ah,
This one
okay. Yes,
and
only
this one.
two vertices. Sorry, I don't
Yeah.
understand. Yes.
And we can make a picture here. It is here, one is here, and we construct this way.
Yes.
This way. Opa. So we have these dual things. It is necessary to. It was remark last time that we are considering what in graph theory is called multigraph. That means that this is not simple graphs, because between only two vertices we have 5 edges. So this is multigraph. Okay.
Yes.
Here we have 3. Sorry. Okay.
Yes.
Here we have 3 domains. 1, 2, and 3. And we have this and this and this. So between two these we have 3 edges, and here is okay. Here we have only 1, right? So this is the dual. All right. A very good thing is here. But again, if we consider dual, then we have 2 vertices and 4 edges. Right. Very good. So this is also beautiful pictures. The whitehead stuff is like this. And here we shall do this thing. Right? A beautiful picture here. But for duals, I should say that it will be, sorry. It will be, if you consider, for example, here, it will be, you see that this is overcrossing, this is undercrossing. So we are moving in this direction. So if we want now this edge, we should put -1 for it. We again will get this thing. And for this beautiful stuff, we have this, and we will get also negative ones. Very good. Are there any remarks or somebody wants to say about these beautiful pictures that we have? I'm trying to download the previous one now. Sorry for that. So I need to return to the last lecture to understand. We didn't finish a little bit the inverse procedure. But to finish with this, it means that we need to discuss the following stuff at the very end. About our graph, the inverse procedure, how to come from the graph to the to naught. So the inverse procedure. Excuse me, my computer is quite lazy. So I sent you the written stuff, so we'll be a little bit briefly today. So me. Yes, so this is, I remind this and the proof and the graphs and this is our construction. Then I think it should be pluses or minuses. Yes, so this is reminiscences of this one, and this one. And now, yes, I'm sorry, this is the old one file. Anyway, now let us consider the next one. Excuse me, I'll try to download it. Today I have problems downloading. So, as actually this is a little bit broad response for what was asked. Excuse me, has some problem. Okay. Do you see?
No.
Do you see the screen?
I can see.
You see?
No.
Don't know what happened.
It's all black.
All black. Yes. Oh, okay.
We see now.
Yeah, very good. Very good. So this is our friend Zoom is doing, I don't know why. So this is the response to the question that you asked, the P coloring. So usually I don't spend time for this, just giving the 3 coloring, but because of your question, I prepared some stuff. Do you see it?
Yes.
So assume that P is a prime, so that we have colors 0, 1, P minus 1, and this forms a field FP. So field, as we already know, it's essential for us. So what will be equations? Sorry. So let us denote three colorings. Let us denote dP of D, the set of colorings of arcs of a diagram with elements of FP, such that at each crossing arc AI, if arc AI is going over and arcs AJ, AK are ones that going under, actually there are two of them, then we have the following equations. If you see that this is the equations, that 2 minus xj minus xk, and this should be equal 0 modulo p. You see?
Yes.
So, of course, it is the same if we'll write the following way, that 2xi is equal modulo p to x j plus xk, right? So you see, this is the form. This is the form, new form of this thing. You see that this is the same if we are working modulo 3, then you see that 2 is equal to minus 1 modulo 3, and you have the same equation that xi plus xj plus xk is equal to 0. Okay. So the same thing, the same theorem, sorry, the same theorem that we have. The same theorem and the proof and everything is the same. So this is the vector space of FP, and if we have two diagrams, they differ by Reidemeister moves, then there is bijection between these two sets. And so the number is the power of P, and this is the link invariant, as well as the dimension of this vector space. So this is the literally the same generalization and the same proof and the same pictures. There are same pictures that we have. If you remember the pictures for Reidemeister moves, they are exactly the same, and they give us the bijection of coloring before and after, only with this equation now, right? So this equation gives us, you see that here it's a little bit, it is not the same geometrically as for three coloring, because in three coloring all colors are equivalent, and here some colors are more equal than the other, right? But the proof by the pictures is the same, so we have this new invariant, which is called tau p. And yes, the proof is, yes, the vector space, the solutions of homogeneous equations, right? The same proof, and the bijection is established by this diagram, right? So let us consider the examples. The number tau 1 is not interesting. Tau 2, sorry. You see what it means, that if you say, if you will have 2x I is equal to x j plus xk, right? But this is 0. This is equal to 0 modulo 2. So you obtain that the color of undercrossing, two undercrossings should be the same. So what does it mean? That it should be, the whole link component should be colored with the same color. And this invariant is nothing but the number of components, connected components of a link. So it's reduced to topological invariant of this. So if we consider now tau 3, this is the same that I already explained, but for other, it is possible to have something non-trivial. So so, for example, our favorite, and Raphael was showing it today, that actually figure 8 knot is 4 colorable, but in particular it means that he is 5 colored. Figure 8 knot is 5 colored. So this is, I prepared the equations, and I took the same colors that we were considering when we were considering the same colors. Yes, so look, excuse me. Yes, the blue x1, red x2, green x3, and black x4, right? So x1, x2, x3, x4. So we have these kind of equations. We calculate the matrix. See, I made the Gauss reduction, but in integers, not in mod 5, but at the moment just for the so here we just eliminate 1, eliminate 2. We have here, so I make this as if we are working over integers. So we have here, and we are getting finally this matrix. So you see, for example, why now that figure 8 is not 3 colorable, because you simply need to make a reduction of this matrix modulo 3, and you have these two will be, of course, the same, and modulo 3, it will be the rank of 3. Modulo other primes, you see the rank will always be 3. So this is the only case, because I made this reduction by integers. So this is the only case that figure 8 knot is 5 colorable. See these equations. So, and we now see that the matrix has rank 2, and so it is the vector space is of solutions has dimension 2. So the tau 5 of figure 8 is 2, and this is the only case because of the matrix of tau of figure 8. You have the 5 this, and this will give you 0 modulo 5. I'm sorry, your pictures disappeared. Do you have pictures, by the way? Rafael, do you have the photos? A little bit strange that I don't have.
Which one?
Sorry. Okay. Do you have questions, dear friends?
No, all is okay.
So this is I prepared that two non-trivial coloring of here is the two non-trivial coloring of figure 8. Different, right? So these are the pictures. So, and this gives us our work gives us the following corollary that you see now that unknot, trefoil, and figure 8 knot, they are 3 different type of knots, because all of them have, for example, unknot and trefoil, they are trivially colorable by 5, for example, and figure 8 is not trivial by 5, and so on. So our work is not in vain. We prove that this 3 stuff is different. So, and this is to finish with our colorings. This is the example of some, so that it is not that other colorings are also sometimes interesting. So you see, this is quite big knot with many crossings. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Quite big. And this is the non-trivial coloring for this sum. Equation will also give us the number 7 somewhere. Okay. Do you have questions at the moment? We finished with the colorings.
All is good.
Very good. So I'll start a little bit with the essential stuff, but please tell me I can finish anytime you want. So as I lost time at the beginning, so I just want to start something, but anyway, you can stop me anytime you want, if there exists. So if there exists at least one participant who wants to show us the end, I will finish. Okay. So the notion of the sum of oriented knots. So the very natural notion that you have the rope and you connect continuously 2 knots. So you need to cut in one place and then to tie them. So suppose that we have 2 oriented knots, K and L. Then we can form their composition. In the literature, you can have the other terms as well. Composition, sum, connected sum, product, everything is okay. So it is obvious way and in following the intuition. So first consider K, then consider L and cut them in several points, in 2 points, here and here. And then make them to, and then make them to be connected. So this way, you see that the orientation is essential. You are going this way, you came to cut, and you continue this way following the orientation here, like so. They should not intersect one over another, just this way and then. So the picture is the following. Right? Yes. So the notation sometimes using this symbol or sum or just a product or simply a point as usual. So anything is okay. So this is what is called granny knot. It has the name. Natalia, especially for you, it has the name. This is the granny knot. So do you see that it is a little bit close to the square knot that we considered today.
Yes.
And what's the difference? Do you
Yeah,
do you
I
see?
do. Here, it's a crossing. Here, the crossing is different.
Right. So you see that if you cut here, if you cut by this line or plane, and you make a rotation, for example, this one, you make rotation for rotation in this direction for 180 degrees. You cut here, and if you want, you join this one with this one with this. If you turn, you'll have exactly this will be trefoil. This will be trefoil. I think it is. So it is left trefoil, right? This is left trefoil. So I noted T minus. And this is also T minus. Anyway, even it may be plus, I may be mistaken, but anyway, they are the same. And for square knot, this is T minus plus T plus. As we shall see soon, that the left trefoil and right trefoil, they are different, they are not equivalent. So you see the same way, using some invariants, we shall see that this knot, the square knot, is different from the granny knot. Okay. Other questions?
No.
So, as you see that we were, sorry, I need to take one. As you see, that, and we shall see that orientation is essential for the for this notion. So we need be a little bit more precise with our orientation. So if we now take a knot, make orientation, and then we take a different orientation, so inverse ordering. If we are describing orientation as the sequence of vertices in the polygon that defines the knot, you take an opposite one, and this is called the inverse or inverted knot, 8 minus k. So, and the knot is called invertible if anyway it is ambiently, or if you want by Rademacher move, is equivalent to its inverse. So then the knot is called invertible. So you see that if there will be invertible knots, then the composition of knots does not depend on the whether you are making connected sum with knot k or connected sum with knot minus k, but it's the same. The only thing we need is to see that everything was done correctly, that the definition was given correctly. Okay. So this is very non-trivial notion, that invertible and its opposite, the non-invertible knot. It is known now that the first, I mean, in the number of crossings and in the ordering of the knot table that we were looking at, this is from Rolfson's. There are several ways, but this is one maybe that was used by Rolfson. So this is the first non-invertible knot. So it means, and it's also not simple to prove. You need to make calculations with invariance, that knots polynomial that we'll study soon. That if you take, for example, this knot, you'll construct. You'll make. Excuse me. I was just. Sorry. Okay. So if you give an orientation to this knot, and take a copy of it with this orientation, and then you take the things like 1811 and with opposite orientation, and it will be, though at the moment we can't prove it, that this is not equal to 817 plus 817. You see, orientation is essential notion for this thing. So okay. understand that this notion is essential, we need the following statement, that the composition does not depend on a point. So we were fixing the construction depends. We are taking points in K, in L, we cut and then joined, but it does not depend. And then it is the same. It looks a little bit at the first time that it is not evident that K join with L is not the same as L join K. This is absolutely evident, and this is also evident that the sum with a knot is gives nothing. You take simply the piece of additional piece of rope, right? So the demonstration is by pictures. So this is, you see that this is, let us first consider the commutativity, right? So this is our K, this is our L. If you need to be, this is like, you may see that this is not, you may consider that they are joined out this box. So what you are doing at first, so and this is the, say, this is the orientation. And what are you doing? At first, you are making either by Reidemeister moves or by delta moves, anything. You are making this knot very, very small. See, it is very, very small. And if you want, you may make this a big one, or anyway, this is almost like a point. You need a microscope to see this knot. And we were making these things when we were looking the delta moves. So, and now you can move, again, you can do this by delta moves, that moving this rope, and this is more small, it has no problem by moving without anything. So, and here in this picture, it is over there. And then it moves outside. Formally, it is this part of the rope is just a circle, piece of circle. And it is here. This is in detail in this picture. And then you are making this small knot the same scale as it was before. You see now, if you look at these two pictures, you see that it is, this is, say, KL, this is LK. So commutativity is proved. And this one is nothing to prove. Other questions?
No.
It's okay?
Yeah, it's good.
So the question may arise, what is the notion of monoid? The only question is, this is the statement of the theorem is that the corollary we already proved. The only thing that we need a notion of monoid. Rafael, do you need to remind what is monoid?
It's a group with something missing. What? Wait, I don't remember. It's a group with one property less. I don't remember which one.
Yes, less. The existence of inverse.
Yeah, that's it. Yeah, so it's a group with no inverse.
So what do we have if we want to construct a monoid? Monoid. We need to have a multiplication, which is formally speaking binary operation. Binary operation. That is for each ordered pair of elements A and B in our M, we associate as A, say, point B. This is what in algebra is called binary operation. And there are axioms. Actually, if you have the axioms A, B, and C equal to A, B, and C, this is associativity. If you just have the set with this operation, then it is called semigroup. Just one property, associativity. Okay, existence of the binary operation, which is associative. So this is the semigroup. And if you have one thing plus, that is the existence of a neutral element, very special element, such that the product A, E is equal to A equal to E A, then these three axioms, I mean the binary operation, which is associative, existence of neutral element, and that's all. Then this is monoid. And then the same, if operation is commutative, the same as in groups, it will be the commutative monoid. So actually, what we proved, this is nothing but saying the same in other words. So the first one is saying that the binary operation is well defined. This is saying that it is semigroup. This is saying that it exists a special element which is called unknown, and this is just one. Okay, and this is commutativity of this. So we proved that this is a commutative monoid. Okay, Other questions at the moment?
And do we try at some point to make it a group or not at all? Because in other field of topology, sometimes we have monoid and we try to make it a group, like
yes,
yes,
yes, you can formally make these, but I don't know what can be done with this group here. In some sense, the essential that it is inside the nodes themselves. There are no any element which can be inverse. So if you have two nodes and you consider the binary operations, the composition, you will never obtain one if at least one of them is not trivial. So in some sense, the object itself is highly non-invertible. So this is actually the semi-group. Very good. And maybe the last property, if you permit the last thing. Is it okay? Or you need that we stop now?
No, you can continue, it's okay.
Yes, so the last one. The last one. So this is about our three colors. So okay. So let us return back to our three coloring. That we have the following formula for three coloring. I remind that this is the dimension of three vector space. So it has the following formula that the tau3 of k connected sum with L, you have the sum minus 1. Okay. So it means that if you a little bit change your invariant, because you always have this trivial coloring for everything. So if you consider tau3 minus 1, then it becomes additive with respect to the composition. So say you add minus 1 here to both sides. Sorry. And excuse me. Oh. Minus 1 here. You see that this stuff, tau minus 1, it is additive. So this is about our invariant. It is almost additive. So how to how to prove it. Let us return to the definition of composite and definition of sum. So if you now consider, say, this one, this is the sum. Let it be the, I don't know why it finished. It's quite strange. I don't understand, sorry. So if you are considering your favorite knot here, and here is another one, say like this, and let T be the number of whole, not just the dimension, but the whole number of coloring of that one. This will be of this diagram, say D1, and here it will be T of D2. No, B, why B? Let it be B. This diagram will be DB. Okay, so when you are making connected sum, you need that this arc will be colored exactly the same color, and that's all. This is the only one constraint that you impose on three colorability when you are making the composite of these knots. So it means that you can make number of three coloring anything you want here, the same, almost the same, but only this one should be fixed, because you are fixing each time you are fixing this. So what it will be, if we consider all colors, it will be like this, but you need to divide by 3, because here one possibility for one arc is omitted. So this is the formula for the number of coloring. So this is our vector space for the composition of knots. So if you now translate this in the level of vector spaces, the dimension of these is, say, tau 3 of K1. The dimension of this is, say, tau 3 of L. And because we need to diminish by 1,3, it means that we're diminishing our vector space by 1 dimension. So you will have this formula for knots. Okay. Other question?
No, it's okay.
Okay. Very good. So I'm sorry, this is I went to this direction, sorry. So this is the result. And now what can we prove? Using these, we can prove the following thing, that now, as we know that so this is our formula, and so now we see, using this formula, we see that there exists this is the connected sum, so not this one. Yes. So we now can formulate, maybe I didn't write it, so that there exists an infinite family of non-equivalent knots. You just can consider you can consider the trefoils. You consider trefoils right or left, doesn't matter. And you can make the compositions of trefoil. You can consider compositions of trefoil. This is just two, but you consider composition with another one, trefoil, and so on. And what do you have if you take n? You will have how many? You have for three trefoils, you have 2 plus 2 minus 1. You have 3, right? And this is exactly why we have for square not equal to 3, because it is the composite of 2 trefoils, right? And so on. So the composition of n trefoils will have n minus 1, right? N plus 1, right? So, and this means that they all are different. So we have different family. We have a family of non-equivalent. So we now understand that there exist at least infinitely many non-equivalent knots, right? So that's all what I want to say today. Excuse me again for very bad dealing with the computer.
Okay.
Thank you.
Thank you.
Thank you.
Okay, thank you. Thank you.
Thank you. Goodbye.
Goodbye.
Goodbye.